Perplexity measures how surprised or uncertain a model is about what word comes next. Low perplexity is good. It means the model is confident and its predictions are focused. High perplexity is bad. The model is uncertain and considers many nonsensical options. The next token predictions here show their possible perplexity scores. Now let's look at context drift. Context drift occurs during long sequence generation. A model may start with the correct context, but one sequence at a time it gradually veers into unrelated topics, effectively forgetting the original context. In this example, we show how the starting context is baking about precise chemical reactions, but each stacked layer has continual context drift, completely losing the original context. It goes from baking to economics. But why does it do this? The problem is computational, regarding how context is stored and retrieved in binary systems. Standard models store context by stacking 2D arrays, token embeddings, into a large tensor, the KV cache. As this stack grows, the original signal, token 1, is drowned out by the noise and volume of thousands of other tokens. The diffusion layered lattice model using SHD-CCP packets do not use stacked arrays. Instead, they work from the outside in, compressing hyperbolically projected data onto the token. This turns the token into a stable attractor for context. Even as new drifting tokens appear, the procedural logic and twistor geometry pull the context back to the central attractor, ensuring stability. There are 4 new conceptual ways we implemented to mitigate perplexity and context drift. The first design goal is deterministic diffusion. The goal of standard diffusion models is to train to denoise a corrupted packet, thereby learning the structure of the coherent language. This is stochastic, as in it adds random noise. A more advanced deterministic alternative is to use physics, such as the Fokker-Planck equation. The deterministic diffusion models create a predictable flow of noise to perform a search simulation. This noise pattern is why we consider this deterministic. By applying a forward-time Fokker-Planck equation, you can expand a single point into a probability distribution over each quadrant of a geometric manifold. In theory, any structured expansion would work. However, prime number sequences, sieves, and lattice structures work well in natural expansion and 3-step compression algorithms. Now that we have performed the forward noising search and the structured expansion discovery, we need to retrace using a reverse process denoising sequence. Since there is an inherent chirality, meaning there is only one path to each node in the chain, and it cannot be broken or the entire chain becomes unusable. This means that if you have performed the first 2 steps of search and discover, you can instantly perform backpropagation through the lattice structure and instantly check for decoherence. The second design goal to mitigate perplexity and context drift was to completely reinvent data transmission protocols and establish a pre-stripped tensor block where context can be embedded. This tensor block is a blank slate but has a pre-established standard called the Symbolic High-Dimensional Context Compression Protocol, which is a comprehensive procedure on how to utilize these packets in any multi-step processing system. 0n Quaternion base time efficiency, combined with 0-1 constant time algorithms utilizing the SHD-CCP packets, we can enable neural-symbolic computation to make the most out of hyperbolic data with the least amount of power. These packets incorporate geometric projection to point to codex positions that store all the compressed data regarding this packet. The higher the rotational compression applied, the higher the context one can compress into a single packet. With clever design, one can fit more codex entries into the projected geometric space than atoms in the observable universe. Geometric projection is only enabled through Quaternion equilibrium states. So why use hyperbolic geometry? Hyperbolic space has more room than Euclidean space. Its volume grows exponentially. When representing hierarchies like compression chains, for multi-step compression cycles hyperbolic space is ideal. Using quaternionic zeros and equilibrium states to orient within this space allows us to mitigate drift by curving trajectories towards stable attractors. Quaternion multiplication allows easy state transitions, because a rotation in hyperbolic space corresponds to a semantic shift. The core procedural predictions will come from learning the rotation quaternion needed to move from one concept to another. For the last design shift, we introduced the 64-bit SHD-CCP packet to replace standard embedding vectors, leading to every packing or token becoming a highly structured multi-dimensional entity, not just a single point or vector in space. Now, the architecture process. The goal of these steps is to go over how to convert raw text into a sequence of clean SHD context compression packets. Clean means they represent a raw concept, with no embedded context. The tokenizer, it's the mandatory first step for everything that involves text. The tokenizer's job is to break raw text into the base atoms for our model. It dictates granularity. The kind of tokenizer we choose directly dictates what those atoms look like. The tokenizer's choice defines our packet lookup table and has a direct impact on the codex and chained truths. To fully realize the potential of these packets, which are inherently hyperbolic, we must transform them into a 4D mind's eye. This not only allows humans to analyze this data hyperbolically in real time, but it allows the simulations required to optimize 4D data to properly interact with each other in simulated non-local space. For every node in the chain, we apply a forward and backwards noising-denoising process while also finding the central sum of the weights through compression twisters. This provides a few important things. Predictable trajectory. As the system learns a pattern, the path in this space will become a tight, predictable loop known as an attractor. This indicates stability and a learned state. The more defined the path, the stronger the prediction. Chaotic exploration. A new or uncertain system will show a wide, erratic trajectory as it explores the state space, searching for a stable pattern. High uncertainty will cause the path to fluctuate wildly. State transitions. A sudden shift from one stable loop to another signifies a phase transition. The system has abandoned one learned pattern and converged on a new one. This makes this geometric diffusion process a literal engine for both context generation and drift stabilization. The linear quaternion backbone, as the denoising engine, uses quaternion rotational neural networks for more efficient geometrically significant stable multiplication. As opposed to standard recurrent neural networks that use matrix multiplication and are computationally expensive. The complete objective is to create a single unified loss function to train the entire model architecture on from end to end. The diffusion structure is the denoising loss that teaches the model the rules of valid SHD-CCP packets. The procedural logic is the loss that teaches the model to follow instructions and chain packets by predicting correct symbolic data or quaternion rotations. The resonance stability is a new loss function that rewards resonance and harmony. It measures chain deviation from a stable, resonant harmonic, penalizing out-of-tune predictions that signify high perplexity. This framework designs a neural-symbolic diffusion model that differs from standard LLMs at a fundamental level. It thinks by tuning a stable 4D resonance field and snapping procedural operations to that harmonic. It can produce a verifiable proof of simulation to trace its output to a genesis truth. This procedural geometrically grounded, cryptographically verifiable approach represents a potential path towards a more robust, compact, and reasoning-capable model for general intelligence.